Okay, good. Thank you. Thank you for the introduction and the invitation. Hi, everyone. Today, I will discuss basically two classes of examples. The first class of examples, these are models obtained by freely acting orbitals of type 2 string theory that preserve no supersymmetry in 5 dimensions. And these are not entirely new models, but were recently revisited in the literature. And then I will discuss models that are obtained from non-freely acting orbifolds of type 2 string theory, which preserve no supersymmetries, but now in 6 dimensions. And this is still work in progress. And to the best of my knowledge, these are sort of new examples. Now, let me start with freely acting orbifolds. And for this talk, I will focus on orbifolds with the following target space. So we have a 5-dimensional Minkowski space times the circles times a 4 torus, which is identified under the action of a discrete ZP symmetry, which we take to be an element of the T-duality group of the 4 torus. And ZP is a cyclic group of order P. And specifically, the orbifold acts by rotations along the 4 torus and by a shift on the circle. And here I denote the complex torus coordinates by W1 and W2, and I also split to left and right movers. And then I parameterize the rotations along the 4 torus by 4 parameters, M1 up to M4. And the definition of the orbifold action is in equation 2, where the left movers are rotated by M1 and M3, and the right movers are rotated by M2 and M4. And the nice thing about this parameterization is that for each of the parameters that are non-zero, then 8 supersymmetries are broken. So starting from type 2, if we want a non-supersymmetric model, we have to turn on all of these parameters. And then regarding the shift, the circle coordinate is denoted here by z, and the shift is simply z goes to z plus 2 pi r over p. R is the radius of the circle, and p is the orbifold rank. And the shift is what makes the orbifold freely acting, because there are no points left invariant under this action, under the shift, which is the definition of a freely acting orbifold. Now, since we break all supersymmetries, tachyons may appear in the twisted sectors of the orbifolds. And this can happen in the NS-NS sector where the 0-point energy is negative. But also in the twisted sectors of the freely acting orbifolds, the windings become fractional, and this is because of the shift on the circle. So if we try to compute the mass of the lightest NS-NS state, which can be tachyonic, then we have a positive contribution to the mass of a state from the fractional winding, and then we also have a negative contribution from the 0-point energy. And this equation 4 is a bit schematic, but still you can see that if the radius of the circle is large compared to the string scale, then these models can be made tachyon-free. However, there is an issue with these models related to the cosmological constant, which classically is 0, but then at one loop, at the quantum level, we compute the one loop cosmological constant, which is negative. And here I have a plot for a particular example, a Z2 orbifold of the one loop cosmological constant as a function of the circle, the radius of the circle. And you see that for large radius, this goes to 0, the cosmological constant, but then for smaller radius, it becomes clearly negative until we hit the critical radius, which is exactly the point where the tachyon appears. So you see that R star is string scale, the order of the string scale, and then actually the cosmological constant diverges. Now, let me go to the second class of models, which are non-freely acting orbifolds. And these are very similar in spirit to some new heterotic models that were discussed very recently. And I think also Khan is going to say some more things about these models. And now the orbifolds look pretty much the same as the orbifolds that I presented earlier, but we just omit the shift on the circle. So we have a non-freely acting orbifold. And here I will also focus in asymmetric constructions. And this means, in terms of these parameters, that M1 should not be equal to M2, and or M3 should not be equal to M4, so that the left movers are rotated differently than the right movers. And now why we want this asymmetric construction is that I will explain, because now, once again, we turn on all these parameters, so we break all supersymmetries, and the question is if there are tachyons in the twisted sectors of the orbifold. And now we don't have any positive contribution from any fractional winding, so the mass of the lightest state is just proportional to the 0-point energy. And since we're doing something asymmetric, you can imagine that the 0-point energy in the left sector is different than the 0-point energy in the right sector. So the situation is that there is a left moving tachyon, let's say, and a right moving tachyon, but these are not actually level matched. And if there is no level matching, then there is no physical tachyon. And this is true all over the moduli space. But once again, if we compute the one-loop cosmological constant, at least at leading order, we find it to be negative. And this is because in these models, most of the massless fermions are projected out, and so we're left with many more massless bosons. So that's all. Thank you.
Okay, thanks very much, George. If there's no ultra urgent question, then we go to the next talk, which is going to be by Khan. So, excellent. Thanks. Please.
All right. Hello, everyone. Thank you for the invitation. I'll talk about some new non-supersymmetric tachyon-free strings we got with our work with Huri Tarazi at U Chicago and Kamran Wafa here at Harvard. To give an overview, I'll first give a motivation to what to look for, and then I'll talk about the 10D non-supersymmetric strings, and I'll talk about the construction method orbitals very briefly, and then we'll present on the new non-supersymmetric strings we found. Now, the motivation is the ambitious goal we have is to describe the real world, which is non-supersymmetric. We don't see any moduli, no tachyons, positive dark energy, chiral matter, and the standard model gauge group. Now, this might be too ambitious. So to make the problem easier, we relax some constraints. We say, okay, instead of no moduli, let's allow one moduli. That's going to be the dilaton. And then instead of the standard model group, let's allow any kind of gut. And we might worry about the dilaton, but there are ways to stabilize it. For example, in our work with Sao and Daniel Robbins in 2022, we can turn on fluxes and get non-supersymmetric ADS. Now let's start our search in 10D, where there are 3 tachyon-free non-supersymmetric strings. First, you have the type 0'b, but it turns out that there are 2 neutral massless scalars, so not exactly what we're looking for. Then we have the USP32. This time there's a massless gravitino that couples to non-supersymmetric matter, so again, not quite what we're looking for. And lastly, we have O16O16 heterotic string, and it turns out that this fits our criteria. Now we ask, what are the lower dimensional analogs of O16O16? We should mimic the construction of O16O16 in lower dimensions. This means we're going to do some orbitals, and whenever we say orbitals, you should think of gauging a worldsheet symmetry that does not necessarily correspond to a geometric symmetry. So acting on holomorphic and anti-holomorphic fields on the worldsheet differently, that would give you an asymmetric action, and that's what we call an asymmetric orbital. Now, a heterotic string on TD is characterized by a lattice gamma 16 plus D comma D, and we can orbifold by the lattice symmetries of this plus some shifts. Now, if we start with E8 cross E8, do a Z2 orbifold, we get O16 cross O16. Let's put it on TD and then choose our lattice so that we get a new ZN symmetry and we can orbifold by it. Then we can get these new non-supersymmetric strings. And in each even dimension, so 8, 6, 4, we can get different kinds of orbifolds. We can get a Z3, Z5, and again a Z5 and 4D, which uses a special quasi-crystalline action on the lattice. We get various kinds of models here, and you can see that in the spectrum here, we have only one neutral scalar, S0 stands for neutral scalar. And to highlight the features of these models, notice that lambda is greater than 0 for all of them. This is the one loop cosmological constant. This is also a feature that is seen in the original 10D 3 non-supersymmetric strings. All of their leading order lambda is positive. Then we have chiral matter for all of these models, and we have some kind of a gut. So for example, for the second one, we have SU5. In 4D, we also have SU3, SU2, U1 inside of a bigger gauge group. And we only have one neutral scalar, and that's the dilaton. So they are rigid in that sense because the charged scalars can't develop a running potential. Thank you.
Okay, thanks very much for the nice talk. So any urgent questions for Can? No? Good. So then we go to the last talk by Alonso. Oh, the screen share failed. It was working before though, no? Yeah. Okay, perfect.
Alonso, you're muted.
There we
Can
go.
you hear me?
Yes.
Sorry. So I'm going to talk about our last work, which is non-supersymmetric vacuum with the fixed moduli. So as we know, string theory allows for additional degrees of freedom, which we interpret as additional space dimension. These additional space dimension give rise also to additional scalar fields, which parameterize the shapes and size of the extra space dimensions. And also this gives the phenomenological properties that we might want. So in order to study and set the asymmetric orbifolds, what we start is with a free fermionic formalism. So what we do is fermionize all the compact boson in terms of real fermions. What we have to do is to assign all the boundary conditions for all the fermions and specify what is the set of basis vectors. This is just to have the complete model in the free fermionic construction. In this construction, the partition function is written at the free fermionic point, so it's fixed here. But the deformation from the free fermionic point, so the deformation of the radii of the tori, is allowed by including the theory interactions, which is this term in the Lagrangian, which is basically this Hij times U1 left current times U1 right current. And in particular, this Hij, this corresponds to four-dimensional scalar fields, or these a combinations of these maybe corresponds to the moduli fields of the compact space. So the important point about the asymmetric orbifolds is that since we have the independence between the left and right moving solutions, what we can do is we can assign a different boundary condition for the left and for the right, such that this Tiering term is not invariant under these boundary conditions. So what can happen is that some or even all of the Walsh-Schittin interactions are forbidden. In this case, all the moduli will be fixed at the free fermionic point. And this is what we have done. So basically what we have done is we started with a heterotic Z2 cross Z2. In the context of free fermionic, we had a nice set plus additional asymmetric basis vectors. What we found was a tachyon free. So we had no tachyons, 3 generations, this kind of gauge group. This is the choice of basis vectors that we had. And what we did was compute the partition function, compute the one loop potential as the integral of the partition function at the free fermionic point, and get the cosmological constant. So we did many examples. In some examples, supersymmetry is broken explicitly, so the gravitino is projected out. In some others, the gravitino is broken a la Scheck-Schwarz, so it acquires some mass. But since the moduli are fixed, the gravitino will continue to remain massive, so supersymmetry is broken. All the moduli are fixed, and we found in some cases a positive, some other a negative cosmological constant. So to conclude, what I want to say is that asymmetric boundary condition as valid as symmetric ones. This gives many new examples, many new possibilities. There are still some problems. For example, the dilaton is not taken into account. Also about tachyon stability, because what we had was a tachyon free at 3 level. What could happen at one loop? For example, a massless state could acquire a mass at one loop, which is negative. And this is what we are looking for with Faraggi and Antoniadis. Also, I wanted to mention this construction from Shio and Tai about massive post-Fermi degeneracy, which can be constructed using asymmetric orbifolds. And thank you.